Hello everyone, we will continue to study the S-domain analysis module of continuous systems. Now, let's continue to study section 4, Analysis Module of Continuous Systems. From this section, we will first learn the relationship between Laplace transformation and Fourier transformation, master the Laplace transformation and its properties, learn how to use Laplace inverse transformation to analyze signal and system performance. Secondly, we will study how to build the S-domain mathematical model of LTI system, and the block diagram of S-domain and the concept of system function. Finally, we will learn how to analyze complex frequency domain by using Laplace transformation and its inverse transformation. The key points of this section are, on one hand, based on elaborating the properties of Laplace transformation and its inverse transformation. We will highlight how to build the S-domain mathematical model of LTI system, the block diagram of S-domain, and the concept of system function. On the other hand, we will introduce the analysis of complex frequency domain of LTI system and its engineering application. In this part, we will introduce the contents from the following aspects. First, Laplace transformation and its convergence domain, and common use Laplace transformation and its properties. Second, we will teach Laplace inverse transformation. Finally, we will teach the concept of system function and analysis and application of S-domain of system. Part 1, Laplace transformation. We had taught time domain analysis and frequency domain analysis of LTI system in the last two parts. Time domain analysis uses impulse signal as the basic signal. Any input signal can be decomposed into a series of impulse signals. The signal state response of the system is the convolution of the input signal ft and the system impulse response. That is, yt is equal to the convolution of ft and ht. Frequency domain analysis first performs a Fourier transformation and turns ft into Fj omega. Secondly, processing signals in frequency domain space and turning Fj omega into Yj omega. Finally, performing inverse transformation and turning Yj omega into Yt in order to obtain system response. Similarly, the continuous system S-domain analysis we are going to tell is similar. First, make the Laplace transformation to change ft to fs. Then, signal processing in the S-domain space, turn fs to ys, and finally reverse transform. Turn ys into yt to get a response from the system. In the frequency domain analysis, one is to break down the signal into overlay of virtual exponential signals, fused series, and fused transformation. The second is the synthesis of response, both the virtual index as a test signal. System frequency domain characteristic Hj omega response is virtual index multiplied by Hj omega. This section analyzes harmonic composition, frequency domain response, waveform distortion, sampling, filtering is very effective. However, frequency domain analysis exists. First, Fourier transformation needs to meet absolute product conditions. Functions such as exponential growth do not meet this condition. Second, Fourier's inverse change solving difficulties thus constrains its applications. Let's talk about the Laplace transformation. If the signal ft is multiplied by the attenuation factor, easy to meet the predictable conditions defined by Fourier transformation. Fj omega equals negative infinity to positive infinity. Ft points of the virtual index multiplied by E multiplied Ft by the product of the virtual index of attenuation factor E. Substitute Fourier transformation formula to carry out the Fourier transformation. We will get the false index of Ft multiplied E, as shown in the formula. Make delta plus j omega equals S. Because S has a frequency volume, we call it a complex frequency. In this way, Fs is equal to negative infinity to positive infinity. Ft times the integrals of e to the power of negative st. This is the Laplace transformation. Let's take a look at Laplace reverse transformation. We know that the inverse transformation of the Fourier transformation is Ft equals 1 of 2 cents from negative infinity to positive infinity, as shown in the formula. We know that the Fourier transformation Ft times e to the power of negative delta t, f delta plus j omega. That is, the Fourier transformation of Ft multiplied by e to the power of negative delta t is changed to 1 over 2 pi minus infinity to positive infinity. F delta plus j omega multiply e to the power of j omega t. Let's multiply both sides, so there is Ft equal to 1 over 2 pi. From negative infinity to positive infinity, F delta plus j omega. As shown in the above formula, we know S equals delta plus j omega. Delta takes the constant to differentiate between the two sides. Then there is equal theory. OK， 这段剪掉。Then there is ds equal to j times the d omega. See the formula as shown. Integral range from negative infinity to positive infinity. According to delta equals j omega, it will be easy to get S points limit. Delta minus infinity to plus infinity. So you get Ft equal to 1 cent of delta over 2 pi j. Subtract j infinity to delta plus j infinity. Fs points for e to the power of st. This is the Laplace reverse transformation. Let's look at the unilateral Laplace inverse transformation. As mentioned earlier, Laplace transformation to Fs is equal to the integrals of Ft e to the power of st from negative infinity to positive infinity. The transformation of t is positive and infinite to negative infinity, and most of actual systems are causal systems. Signals are called signals if the zero system is used at this point. T transformation is from negative infinity to positive infinity. It becomes from 0 negative to positive infinity. Then the Laplace transformation becomes Fs minus dt from 0 negative to infinite Ft e to the power of st. Ft is called the original function, then Fs is called the image function. From Ft to Fs, we call Laplace transformation, that is, the image of function. From Fs to Ft, we call Laplace reverse transformation. It is also known as the original function. Let's look at the relationship between the Laplace transformation and the Fourier transformation. We said earlier that ft times e to the power of delta t make Fourier transformations, equivalent to a bilateral Laplace transformation of ft. When delta equals 0, s equals j omega, then it becomes s equals j omega. At this point, a bilateral pull-up transformation of ft. It becomes a Fourier transformation to ft because of the causal system when t is less than 0 ft equals to 0. Fs equals negative infinity to positive infinity. The integral downline becomes 0. At this point, a bilateral Laplace transformation of ft turned into a unilateral Laplace transformation. Okay, this part of the content is explained here. Thank you.